Okay. Surprising, lot of people have not joined yet, huh?
आपने बोला ना सर आज कुछ खास नहीं है.
Okay.
स्कॉलर लोग है सर.
Sir, I have one doubt in question number 5. Just in case before starting, we can just clear this thing out. सर उसके अंदर जो P का वैल्यू है वो मेरा 97 आ रहा है सर.
Just a minute, beta. Just give me 1 minute.
And you have shared the solution as well. That's why I was little hesitant to ask the doubt.
No issues. I believe some people are having issues joining. Let me share the link with them. Okay, all right. They'll join. Go ahead, beta. Which question are you having doubt in?
Sir, in question number 5, if you have the solution handy in front of you, you can directly open it.
Okay, I'll do that. I'll do that.
Question
Number 5. Huh?
5 in the PDF, page number 9, I suppose. 10. Question number, page number 10 and question number 5 solution. Sir, the value of
Let me open it up. Let me open it up.
Okay, sir.
Okay, number 5. Huh?
Yes, sir. We can next page from here. Not the starting, next page. Okay, here. Okay, after we have calculated A, in the where your marker is present, there is you have shown the calculation for the angle P, which is in my case it is coming 97 degrees, 97.87, because the value of A is more than 90. So in the second step you have written tan of 6.741. You can write, you can observe that.
That's okay, beta. Is the answer matching? The final answer?
Final answer is not matching, sir, because in my case the P is coming about 97 degrees and yours P is coming 7.87 something.
Okay, all right. Let's see. Sine of 90 minus PA. 90
Yep.
minus PA is basically the latitude of A.
Yes, sir.
So the latitude of A is 5842. So that's all right. Sine of 5842. Tangent of 90 minus P, this needs to be calculated, and tangent of 90 minus A.
So the value of A is in this case is more than 90, that is 96 degrees something. You can see in the above page. Value of A is coming 96.741 degrees.
P नेगेटिव में आ रहा होगा ना -6 समथिंग.
हाँ. P नेगेटिव में नहीं आ रहा है, P पॉजिटिव में आ रहा है, बट 97 आ रहा है. P नेगेटिव में नहीं आ रहा है, पॉजिटिव में ही आ रहा है P.
Okay, all right. What is the longitude which you are getting, beta?
So longitude, just a minute, I saw it somewhere. Sir, longitude I did not calculate because the P was, I was confused with the P stuff. That's क्योंकि उसके अंदर tan negative में था.
Okay, I'll need to check it, beta.
7 degree, 52.5 minutes.
करेक्ट सर 752.6 आ रहा है P1 और आंसर मैच हो रहा है सर, किया मैंने.
हाँ, आंसर मैच हो रहा है.
Okay, so just share your solutions with them.
Yeah,
आंसर मैच हो रहा है सर. एक चीज बता दो बस इस क्वेश्चन में.
हाँ बेटा बोलो.
सर ये P जो है ना सर, यहाँ पे हमारा A आया था 96 डिग्री, ठीक है सर. तो इसमें इन्होंने जो 90 माइनस A लिया है ना सर, आप देखिए सॉल्यूशन में 6.741 लिया है. 90 माइनस A इज इक्वल टू 6.741.
राइट.
ठीक है सर, बट A की वैल्यू 96 है सर.
ओके, ऑल राइट बेटा.
हाँ जी, वो बता दीजिए बस.
सर इसको ऐसे कर सकते हैं, जैसे सर मेरा जो एंगल ए आया था वो 83 समथिंग था डिग्री पी ए बी ट्रायंगल में, तो जो एंगल ए होगा इन राइट एंगल ट्रायंगल वो 180 माइनस ए कर देंगे तो सर 90 कुछ आएगा सर.
Just give me a minute बेटा, let me check it up.
उससे सर पॉजिटिव में आता है फिर एंगल ए ना सर, फिर कंफ्यूजन नहीं रहती सर उसमें.
directly we can use that na sir. Tan 90 minus theta equal to cot theta. Cot theta is 1 by tan theta. That's it.
No, that's right.
सर ऐसे कर सकते
So
हैं,
it will be
ए बी
tan
में जो
96.
एंगल ए आया सर उसको 180 से माइनस करेंगे तो आउटसाइड एंगल ए आ जाएगा सर, राइट एंगल ट्रायंगल वाला सर.
So that negative doesn't make a difference actually, even if 90 and A is 96, no? Because tan 90 minus A is something. So even if we get minus, we can neglect the minus and it's okay.
But I don't think so, because you know in trigonometric point of view से अगर हम माइनस पे डालेंगे तो कैलकुलेटर सही आंसर देगा. Sometimes we can neglect, sometimes we cannot neglect.
And 90
Okay,
minus.
beta,
No, no,
do
tan
one thing.
90 minus
Do one
theta
thing.
is cot
Hold
theta.
on. Do one thing. बेटा आप अपनी नोटबुक में इसको वर्कआउट करो. Okay, and instead of 6.741 you are saying it is minus 6.741, you put it as minus, right?
हाँ सर, करेक्ट.
हाँ, आप इसको वर्कआउट करो and tell me what is the value of P which you are getting.
एक सेकंड सर.
सर मैंने
please.
ग्रुप में सेंड किया, अभी जो सॉल्व किया हुआ है.
Have you worked this out?
तो वही
हाँ
आएगा.
यस सर यस सर.
So it will be same. No minus. P will be minus, sir.
So are you getting P minus 7.876 or you are getting it
No
plus
sir, I'm
7?
getting positive.
Yeah,
I'm
that's
getting
right, beta.
positive ones.
That's right. There is a minus which is missing here, but the answers are correct.
Yes sir.
1 second,
Yeah,
sir.
you,
Hold.
yeah, you can work it on the calculator, beta.
सर इसको ऐसे कर सकते हैं सर, जो एंगल ए आया दैट इज 96
हो
डिग्री.
सकता है
कैसे
सर,
बेटा?
सर एंगल ए निकला मेरा 96 डिग्री 44.49 इन ट्रायंगल पीएबी. एंगल ए निकल गया मेरा सर.
ठीक है जी, ठीक है.
फिर उसको सर मैंने ए को एंगल दैट इज इन ट्रायंगल पीबी सर एंगल आया 96 डिग्री, तो उसको मैंने 180 से माइनस किया तो आउटसाइड एंगल निकल गया सर मेरा वो.
You mean to say this particular angle?
सब्ट्रैक्ट फ्रॉम 180 डिग्री सर. यस सर.
This one?
नाउ इट विल 83 डिग्री सर. ये 83 डिग्री समथिंग आ जाएगा सर.
Right.
तो मैंने इसे सोल्व किया सर, कुछ नेगेटिव भी नहीं आता और आंसर भी सही आ रहा है सर.
हाँ ठीक है बेटा. You can do this way also. Perfectly all right. You will get the answer.
क्योंकि सर इनर ए एंगल मेरा निकल गया 96 डिग्री, उसको मैंने 180 से माइनस किया तो जो आउटसाइड ए है इट विल कम 83 डिग्री समथिंग सर.
हाँ that's right बेटा. You can do that.
हाँ सर.
हाँ जी बेटा बोलो.
हाँ जी सर, उसको जैसे आपने बताया अभी वैसे सॉल्व किया तो ये इसमें जो इक्वेशन है कहाँ गई सर? साइन ऑफ, हाँ ये जो सर पी आ रहा है ना सर, वो 172 डिग्रीज 7 मिनट्स आ रहा है.
अरे बेटा दोबारा चेक करो. P नहीं आ रहा है ये.
नहीं
Check
सर,
it
अगर
again.
tan को माइनस 6.741 लेंगे तो आएगा सर.
Yes, sir. That's right. Correct. He's right, sir. How can we get a positive P if your tan is minus 6.741?
Okay beta, hold on. Let me open up the whiteboard. Okay, so let's do it here.
सर P की वैल्यू मैक्सिमम कितनी हो सकती है?
एक मिनट बेटा, पहले इसको कर लें फिर उसके बाद अगले क्वेश्चन. ये आंसर नहीं आया ना
वही
आपका.
सर 180 से माइनस करेंगे ना, जो P की वैल्यू आ रही है 172.
एक मिनट बेटा, अब तो मैं कर ही रहा हूँ ना. आप थोड़ी शांति रखो. लेट अस कंप्लीट देन वी विल मूव अहेड.
अच्छा सर ठीक है सर, आप देख लीजिए.
Very good. Sine of 5842 is on this side divided by tangent of minus 6.741, right?
Yes sir.
Equal to tangent of 90 minus p. ये सही है बेटा जो मैंने लिखा है?
tan of 90 minus p. हाँ सर सही है.
ठीक है सर.
वेरी. अब कैलकुलेटर में बेटा ये डालो और मुझे बताओ 90 माइनस p की क्या वैल्यू आ रही है?
सर
इशू क्या है ना सर, जब
आ रही है -82.14.
Yes, sir. Minus 82.1.
जो
Okay, just hold on.
एंगल 96
hold on. बेटा रुक जा, एक मिनट रुक जा. आंसर बताओ बेटा.
-82.14 and that gives us P equals to 172 degrees 8.9 minutes.
Hold on बेटा, रुक जा. ये -82.14 है.
Yes, sir.
Correct sir, correct.
Yes, sir.
Correct. Okay. Now I take P to this side. It becomes a positive P.
जी.
Okay. So this angle is coming to what value now?
172.14.
Just a minute.
सर इसमें ये करना ही नहीं पड़ेगा सर आपको.
एक मिनट बेटा, एक मिनट रुक जाओ.
इसको 180 से माइनस करते हैं, सही आंसर आता है सर.
Arey, but point is we can get 6, but it should be a right process, no? To get
सर
6.7.
मैं बताता हूँ सर जो आप 96.44.5 ले रहे हो वो एंगल PAX है, बट जब अपन सोल्व कर रहे हैं तो ट्राइंगल PAV1 बन रहे हैं। जब PAV1 करोगे तो आप 96.44 ही लोगे, वो एंगल आप लोगे 180 माइनस 96.44.5, वो एंगल उल्टा ले रहे हैं अपन जब कैलकुलेट कर रहे हैं तब।
Yes, that is right actually. Sir, 96 लेके ही कर सकते हैं।
जो PAV है ना सर,
that's right. Exactly beta, exactly what you are saying is right. What you are saying is right.
एंगल A PAV लोगे ना तो 180 माइनस 96,
that's right beta, you are correct.
Yes sir.
ये ट्रायंगल जो है ये PAV है बेटा, this is PAV triangle. PAV triangle का जो एंगल है that is this particular angle, not the inner angle A which you calculated. So that has to be 180 minus this beta.
Yes sir.
So 180 में से इसको subtract करो और उसे यहाँ पे use करो।
That will come 83 degree something sir.
नहीं आएगा सर, 7 डिग्री 52.6 आ रहा है सर।
समझ गया बेटा?
समझ गया सर। थैंक यू सर, थैंक यू लोकेश।
वेरी गुड। अब बेटा एक काम करो, तुम जो कर रहे हो ना, आई गॉट टू नो वेयर द प्रॉब्लम इज। प्रॉब्लम ये है कि तुम सोल्यूशन को देख के उसका सोल्यूशन निकाल रहे हो, वो मत करो। तुम पहले अपना सोल्यूशन निकालो और फिर अगर आंसर मैच नहीं होता है तब मैच करो, राइट?
ओके
yes sir, one more thing sir, instead of taking triangle PAV,
right,
I've taken to find out PV, I've taken triangle PBV.
Yeah, you can do that beta, you can do that. You can take triangle Papa Bravo Victor also.
I'm getting little slight different answer. 31 degrees 1.3 minutes is PV what I'm getting.
Should not be beta, should not be.
Hyla. Okay. I'll check again.
Okay, just a minute beta, let me just go on the group and check what is the status.
लोकेश
हाँ भाई, हाँ जी।
लोकेश, हाँ तो करेक्टेड स्टेप क्या लिखे? tan 90 माइनस A माइनस 180 करना है क्या?
जो एंगल A है ना, एंगल A की वैल्यू आप अगर नेपियर रूल लगाओगे तो आप P1 में नेपियर रूल लगाओगे। जब ट्राइंगल PAV1 में A की वैल्यू 180 डिग्री माइनस 96.44.5 है, तो वो 90 से कम है।
ओके ठीक है सर।
sin 90 माइनस P अपॉन sin 90 माइनस A इक्वल्स टू tan 90 माइनस P लगा दो फिर आप।
ओके ठीक है सर, थैंक यू।
बेटा आई स्टिल हैव डाउट, ये बच्चे किसी और लिंक पे तो नहीं चले गए हैं? Have they gone to the previous link, old link by any chance?
किसी और लिंक पे जाते तो मैसेज कर देते सर। हाँ, आपको ढूंढते आप मिलते नहीं तो मैसेज कर देते ग्रुप पे।
हाँ, आई एम सरप्राइज्ड, काफी बच्चों ने ज्वाइन नहीं किया।
सर सेम इशू एक दिन मेरे साथ भी आ रहा था। मैं बार बार लिंक जब सेलेक्ट कर रहा था तो जब मैं ग्रुप लिंक ओपन हो रहा था तो सिर्फ एक ही 2 लोग शो कर रहे थे। तो उस दिन मैं 7 o'clock से अराउंड 8 o'clock तक मैं ज्वाइन ही नहीं कर पाया। I don't know what was the problem. I thought it was the problem with my phone. I switched it off and on, but still I won't be able to connect.
Okay beta, okay, let me check. I'm just going to the other link and seeing if people are there. Let me just go out and come back again.
सर मैसेज आ जाता अगर नहीं होते तो।
That's right, no message is also there. Yeah, people are not there also. But little surprising, beta. Never happened before. So many absents.
सर अगर उनको परेशानी हो रही होती तो अब तक ग्रुप पे मैसेज आ गए होते. We should start. Means अभी तक तो
Okay,
do
all right. That's right. Okay, beta. Okay. So there's a mention of rump line sailing. I will tell you today. We will cover up the plane and parallel sailing and Mercator sailing, so you'll come to know. Okay, we'll do that. So let me just check it once more. Just give me 2-3 minutes, beta. Then if nobody else is joining on, then we'll start off, right? Beta, there is some issue with
Hi
our.
guys, good evening. Sunil, how are you?
Good evening, sir. Good evening. I can hear you, but cannot
Yeah,
see
I
you.
can see. I can see 37 of them. I think that you're missing out on the list somewhere.
Right, sir. Right. I'll just log out and log in
I
again.
think they are there. You can log out and log in again and then resume the class, I think. Okay.
Ji, sir. Ji. Right.
Okay.
Right, sir.
Okay.
Thank you, sir.
Thanks.
Thank you.
Hi, batch. How are you? All good?
Yes, sir.
All good, sir.
All good,
Yes, sir.
Yeah, I think
All good,
Baba
sir.
is having some problems. He was able to see only 3 members. I think he's just rejoining. Just wait for a while, guys.
Okay, sir. We are waiting.
Yeah.
Okay, beta. Great. So there was some.
Okay, now you can see them. Okay. Okay, fine.
Sanji,
Take
now I
care.
can see them.
Okay,
I
I'm
can see
signing
them.
out. Take care. Bye.
Ji. To see me and hear me before also.
Yes, sir.
Yes, sir.
I
Yes,
was
sir.
out with you,
Yes,
sir.
sir. It was
Okay.
okay, sir.
Okay, all right. I
Yes,
was
sir.
not able to see anybody, so there was some glitch with the software. Anyway, so it's okay now. Okay, beta. Great. So, any more doubts, beta, you have?
Sir, in the question 5, when we were solving, after calculating the initial angle, sir, so why we were need to calculate the vertex? Actually, that time when I was solving, no, that time I was facing this issue. So if we are crossing 15-degree longitude west meridian, this is coming after 5-degree west longitude. So it would be, I think, not spherical triangle if we are doing with that method. If we are putting this meridian in between that A and B.
Okay, beta, let me understand your query. Let me open up the solution. Just give me a minute. Okay, you are talking of number 5, beta. Can you please repeat the doubt?
Yes sir. सर जो ये 15-degree longitude meridian है ना, जो ये मतलब after this will be coming after 5-degree west longitude, no? So why we need to calculate the vertex first?
Okay, beta. So A is at 005 west. That's right. B is at 064 west. Let's write it here. 064 west. Certainly 15-degree west will be coming somewhere here, right? So your question is that why do we need to calculate the vertex first, right? Calculating the vertex, how are you going to find this point? ये x point है हमारे पास. So without finding the vertex, can you tell me any method with which we can find this?
No, sir. Actually, I was also facing this issue because there was no method, because we were not knowing the two sides actually, PX and AX. We are not knowing that. So
Exactly. So you have answered your doubt. There is no
yes.
method without calculating the vertex to get to this. That's why we are calculating.
Yes, sir, जाके just ऊपर.
No, beta. No. It should not be 90 degrees. That's a mistake. Yes. No, it will not be 90.
Okay, sir.
Okay.
Hey, right now, Ankit Mahajan क्या?
Say again, beta.
Sir, I have one doubt on the same question. This triangle PXA, we know the D long of the this triangle, so we know the angle P.
Yes, that's right. We know angle P.
And in triangle PAB, we can find angle P.
Yeah, you can find angle P. This one,
yes.
you can.
No, sir, the another one, triangle PAB, the right side.
PAV, Papa Alpha Victor.
Yes, sir, PAV, Papa Alpha Victor.
Yeah, you can find angle P. That's right.
And for calculating the position of PX, the side PX, to know the latitude of X, can we add these two V's, these two angle P for calculating, taking triangle P, X and V vector? Yeah.
So you get this angle, right? Yes. This is a right angle here.
Yes, sir.
And you also get Papa Victor. Papa X-ray, that
yes.
gives you the colat and you get the latitude of X.
Yes, sir.
That's correct, beta.
We can do that.
You can do. Yes, why not? That is what is done actually.
I'm getting little different answers, sir. I'll check again and do it again for this.
Okay, all right. Must be somewhere in the calculation. Otherwise, the method is correct, beta. That is what should be done. In fact, that is the only method.
Okay, sir.
So I have some problem in question number 19, sir. 19.
Question number 19. Okay, let's go to 19.
Yeah. While calculating the longitude of vertex, the last step. Right. I'm not getting, sir, actually how it is.
This one, beta?
Yes, sir. Can you explain, sir, from P equal to D long, V to V?
Okay. Okay, all right. So beta, what we have done here is, just a minute. First, we have obtained the vertex. Latitude of the vertex is obtained. Then for getting the longitude of the vertex, so we are using Papa Bravo vertex triangle. This angle is 90 degrees. Angle B is known to us and Papa Bravo is known to us. Okay, so angle B is known to us, Papa Bravo is known to us. These are two tick marks. And what we are calculating is angle P.
Position of vertex only, sir.
Yeah, so what doubt you are having, beta, in the application of Napier's?
No, sir. How we get the D long? How the direction of the D long? I mean longitude of vertex.
Okay, beta. Are you able to calculate this angle P as 9900.7? Are you able to do this much by applying the Napier rule?
Yeah, I already done that one. That much.
Very good.
Up to that.
So this is got up to here, no doubt, right?
No.
Very good. So that basically tells us that this angle here is 99 degrees. 0.7 minutes. This is the angle which we have found out. Now you see, beta, the longitude of Bravo is known to us. We know what is the longitude of point B. And this angle which we have found out, this is the D long between Bravo and vertex. Correct?
Yeah, correct.
So longitude of Bravo is 122 degrees 25 minute west. This is given in the question.
Okay.
Vertex is 99 degrees 0.7 D long away. And from B, you need to go westwards. So this D long is also westerly, correct?
Yes, sir.
Right? The left side direction is the westerly direction. So longitude was westerly, D long was westerly. So we added both of them. And when you add both of them, you will get a value which is greater than 180. So can you do that in the calculator and tell me what is the value you are getting?
So 1 degree 25 minutes.
Very good. Now longitude cannot be greater than 180. So if we get a value more than 180, what do we do?
Minus 360.
Yes,
yes, sir.
and change the name.
Yeah, sir. I only problem in that, sir. While this, I understand now how to take the direction of D long. For this, okay. That arrow marks.
No problem, beta. Remember this cross. Always remember the right side is easterly direction and the left side is westerly direction, whether it is the chart or our answer sheet, anywhere. Right side is easterly, left side is westerly. That's number one, correct?
Yeah, correct, sir.
Correct. And now if you want to make this PAB triangle, if you are having issues, where should be B with respect to A or A with respect to B, we have to get the D long. So A's longitude is 166.30 east, B's longitude is 122.25 east. So बेटा आप मुझे बताओ इन दोनों में D long कितना है? ये हमने कल भी किया था.
Yeah, sir, this I understand, sir, already. My problem is that when we have one D long and one longitude of other, so how will find that longitude of third one?
Okay.
That's the problem, sir, I'm facing.
You have the name of the D long known to you. That is no issues, right?
Yeah, that I understand.
Okay. The D long name basically tells you in which direction you are proceeding. If you are at 122 degrees west and you are proceeding 99 degrees west, obviously they should be added up. If the names are same, they will be added up. If the names are opposite, it will be subtracted.
Okay, so it is same in both the cases, right? If we have longitude of B and D long, and other case also if you have longitude of A and longitude of B, whatever it is, this funda is same, right?
That's right, beta. That's right.
Okay, sir. I have problem in that only. Okay, sir. Thank you, sir. I clear my doubts. Thank you.
Okay. All right, beta. Okay. So let's close this out now. Even if you have some questions pending, you can keep on doing them. And if any more doubts come, we will discuss them in subsequent classes. So let's now go into today's topic. Today is a simple topic. We are going to refresh our knowledge of pre-C as well as second mates so that we are ready for phase one. So I'm first going into sailings, beta. We have already done parallel sailing, composite sailing. I told you parallel sailing formula. Departure is equal to D long into cos of latitude. Okay, so parallel sailing is very simple. We only use that particular formula, and we have done the composite track calculation using parallel sailing. So now we will be seeing plain sailing and Mercator sailing. So all these three sailings, parallel sailing, plain sailing, and Mercator sailing, they are known as rumb line sailings because they give us rumb line distance between two places. What is a rumb line? Rumb line is basically a straight line on a Mercator chart. So let's go into plain and parallel sailing. That is our second form of sailing. Let me set up the presentation. Now moving on to the second rumb line sailing, that is the plain sailing. So how does the plain sailing gets its name? Now, initially, when the navigators started moving into the seas, long time back in the history, when we started making boats and started venturing out into the sea, we were not having any high-tech instruments to find the courses and the distances. But in those times also, we had the knowledge of trigonometry. Trigonometry is basically the solution of a right-angled plane triangle. So we were aware of how you can calculate the sides, the angles of a right-angled plane triangle. And the sailors used this same knowledge, that is the knowledge of plane trigonometry. There is two branches in trigonometry. One is the plane trigonometry, another is the spherical trigonometry. Plane trigonometry is for calculating on plane surfaces. Spherical trigonometry is for calculating on the surface, curved surface of a sphere. The great circle sailing and composite sailing use the concept of spherical trigonometry. But as I was telling you, in the olden days when navigators ventured into the sea, they wanted to calculate these courses and distances, and they had the knowledge of trigonometry available with them. So what they did was they used the same trigonometry knowledge to calculate the courses and distances between two positions. So how did they do that? They basically made a right-angled triangle, a plane right-angled triangle involving the initial position and the final position, and they solved it using trigonometric ratios. So that's why the name given to this particular type of sailing was plain sailing. Now, going into trigonometry, we are aware that there are three different ratios in trigonometry. We have the sine theta, which is equal to perpendicular upon hypotenuse of a right angle triangle. We have the second ratio as cos theta, which is equal to base upon hypotenuse. And we have the third ratio as tangent theta, which is equal to perpendicular upon base. All three referring to the plane right-angled triangle. So let us see now, how did we use these three trigonometric ratios, sine theta, cos theta, and tan theta, to calculate our courses and distances at sea. Let's assume that the vessel is right now at this particular position. You can see the position on the screen now. Let's mark it as A. This is our initial position or the starting position. Let's assume that the vessel wants to reach at this particular position displayed on the screen now. I'm highlighting it with my laser pointer. So this is our destination position. Let's mark it as B. This is our final position where we want to go. Now our main aim, we know what is our initial position. We know what is our destination. Our main aim here is to find out what course should we steer to arrive at our destination B. And the second thing, what distance should we be steaming to arrive at our destination? Distance is required because you need to fuel up basis that particular distance. You need to have the supplies, fresh water, provisions, food as per that. So these two are the important things which we want to find out. So how do we do that? We basically involve these two positions in making a right angle triangle. How do we make the triangle? Let's see. You can see a right angle triangle being made. Our initial position and final position are the two vertices of this right angle triangle. Now we want to approach our destination position B starting from A. So the arrow shows the direction in which we are proceeding. And this side of the triangle, that is AB side, is basically representing the distance which we need to cover to reach our destination. So this is one of the items which we are required to find out. Now let's name the third vertex of the triangle as C. Now this angle which you see here, this is angle A. This is the angle between true north. You see AC line is pointing towards true north. It's a vertical line, and the direction of true north on our chart is vertically upwards. So AC line represents the true north, and AB line represents the direction in which the ship's head is. So this is the angle between true north and the ship's head. This is basically our course. So let's mark this angle as course. This is the second item which we need to find out. Now, if you take your attention to the vertical side of this particular triangle, that is AC, Alpha Charlie, this vertical side of the triangle on a chart basically represents the difference of latitude, in short known as D-lat. This is the D-lat between our initial position A and our final position B. If you plot these two positions on the Mercator chart and you measure this up and down distance, that is alpha to Charlie, it will give you measure it on the latitude scale, it will give you the D-lat, or it will be equal to the D-lat between the two positions. Now the horizontal side, which you see, the topmost side of the triangle, is the departure between A and B. So if you see on a Mercator chart, it is the east-west distance between these two positions, the starting position A and the destination position B. And this east-west distance between the two positions is known as departure between them. So we have the triangle labeled now. We know all the three sides. We know one of the angles. Now in this triangle, the angle C which you see, angle C highlighted on the diagram now, is a right angle. It's a 90-degree angle, as AC represents a vertical side, Bravo Charlie represents a horizontal side. So we have a right angle triangle here. Now considering this angle as our course, that is angle A as our course, the side AB of the triangle is the hypotenuse. Hypotenuse is the side opposite to the right angle. So side AB is the hypotenuse. Side alpha to Charlie AC, which is connected with this angle, is the base as far as trigonometry is concerned. And the horizontal side, that is Bravo Charlie BC, is the perpendicular. So we have identified the three sides. Distance is the hypotenuse, D-lat is the base, and departure is the perpendicular. Now let us apply the three trigonometric ratios to this triangle. Let's first apply the ratio of cos theta. In this case it will be cos course. Now we know cos theta is equal to base upon hypotenuse. So cos of course becomes the difference of latitude, or the D-lat, which is the base, upon distance, which is the hypotenuse. Now this ratio, trigonometric ratio of cos course, gives us our first formula for plain sailing, and that formula is D-lat equal to distance cos course. We have just taken the distance to the left hand side. So on one side you have the D-lat, on the other side you have distance cos course. So this is the first important formula we have for plain sailing. D-lat equal to distance cos course. Now let's go to the second trigonometric ratio, that is sine theta, in this case sine of course. it is equal to perpendicular upon hypotenuse. So sine of course is equal to departure, which is the perpendicular, upon hypotenuse, which is the distance. Now this ratio gives us the second formula for plain sailing, that is departure equal to distance sine course. So this is the second important formula for plain sailing, departure equal to distance sine course. Now let's go to the third trigonometric ratio, that is tangent theta. Now in this case it is tangent course equal to perpendicular upon base. In our case the perpendicular is the departure and the base is the d lat. So tangent course is equal to departure upon d lat. This is the third important formula which we have for plain sailing. So you see the three trigonometric ratios, cos theta, sine theta and tangent theta, gave us the three formula which we use for plain sailing. Now these three formulas help us to calculate the course and distance if we know our initial and final positions, the departure position as well as the destination if it is known. We can easily calculate what is the course and what is the distance. Now it can also be used to find out the position arrived in case a certain course and distance is followed. Let us say we know that we started from position A, we were moving on a certain course, we have a certain distance. We can easily find out with this course and distance what is the position where we are going to arrive. So these are the two most basic simple calculations which can be easily done using these three formula. Now just to give you a lead, if you know the initial position, you know the course and you know the distance. If you apply the first formula, the course is known, the distance is known, you can get the d lat. If you apply this d lat to your initial latitude, you will immediately get the final latitude. Now when you come to the second formula, we have the distance, we have the course. So when we put these values, we can easily calculate the departure. Now once we have the departure, we can convert it to d long easily by using the parallel sailing formula which we saw just a little while before. Departure is equal to d long into cos of m lat. So once you convert it into d long, apply it to the longitude of your initial position and you get the final longitude. So a two-step calculation to find the position arrived. In case both the positions are known to us, you can easily find out the course and distance also. If both positions are known, you can calculate the d lat. The d lat can be calculated. You can also calculate the d long, which can be converted into departure. With departure and d lat, you can apply the tan course formula and it will immediately give you the course being followed. Once the course is known, you can go to formula number 1. You can put the course here, you can put the d lat value here, and you can easily calculate what is the distance between the two positions. So that sums up the plain sailing. Important thing to note here is that the triangle which we have made, this particular triangle, is made for the northeast quadrant. For every different quadrant, we have a different triangle. I'll show you a little while later the triangles for other quadrants also. But this is the one which we use for northeast quadrant. You can see the vessel is moving on a northeasterly track. And important thing to remember here, the course which we use in any of the triangles is the quadrantal course. It will become clear to you when you see the other triangles also. So the course which we use or which we obtain from the formula will always be the quadrantal course, not the three-figure notation course. So beta, I hope clear up to here. Can we move on to the next slide?
Yes, sir. Yes, sir.
So just one thing, the catch is also that we cannot use this formula for distance more than 600 miles, right?
Right, beta. That's right. That's right. I'll explain to you.
सर इसमें 10 कोर्स में that course will be sir quadrantal course ना sir?
Always, beta. It will be quadrantal course always.
We have to convert it to course later on.
That's right. That's right.
Okay sir.
Okay.
And sir, departure will be equal to d long cos mean length, correct?
That's right, beta.
वो भी इसी में ना सर प्लेन सेलिंग में.
That's right, beta. That's right. The same formula which we used in parallel sailing is used in plain sailing also. The only difference is latitude becomes mean latitude. Mean of the both position latitudes, that is what is used. Departure is equal to d long into cos of m lat.
And sir, that formula, the departure cost d long cos mean length, can we use for more than 600 miles?
Yes, that formula can be used for any distance, beta. For parallel sailing, okay? For parallel sailing,
Okay.
when you are moving along the parallel on a easterly or westerly direction, you can use it for any distance.
Okay, sir. Thank you.
And for plain sailing, we can use this for up to 600 miles, right, sir?
That's right, beta. Up to 600 miles.
Okay, sir.
Okay, let's move ahead.
So with this question, which question number are we targeting in the question paper right now?
Okay, beta. In the question paper, we are now targeting question number 5 and 6. Both these questions we are targeting. 5 and 6 questions are based on number 1 side solving and number 2 plotting. One of these questions is on side solving. So 5 methods of side solving are there. And one of these questions is on plotting, staggered and simultaneous plot. So all these things which I am covering now will be required in number 5 and number 6.
Perfect. Thank you. Yeah.
Okay, beta. Let's go ahead. Now, as I told you that we have different triangles for different quadrants. Let's see the triangle for other quadrants also. The triangle which we just now saw was this one, that is the triangle for northeast quadrant. This angle was the course, this side was the distance, horizontal side departure, and the vertical side was d lat. Now, if the ship is moving on a southeasterly course, then the triangle which we follow is this one. This position represents our starting position. This position here represents our destination. This side, the hypotenuse, represents the distance. The vertical side is the d lat, and the horizontal side at the bottom is the departure. Now, if you look at the course angle, which is this particular angle here, it becomes clear to you that the course which we should be using in this sailing is the quadrantal course. So you see the course or the angle is measured with reference to south direction. This is the angle between the south direction and the ship's head. So this is the quadrantal course. South so many degrees east. Similarly, for southwest quadrant, you see this is the particular triangle. This is our starting position. We are moving in a southwesterly direction. This is our destination position. The horizontal side is the departure and the vertical side is the d lat. And this particular angle is the quadrantal course. South so many degrees west. And this triangle which you see is the triangle for the northwest quadrant. This is our starting position. We are moving in a northwesterly direction. This is our destination. Then the horizontal side is the departure and the vertical side is the d lat, this angle being the course. Again, quadrantal course, north so many degrees west. So these are the 4 different triangles which we use for calculation in plain sailing. Now, one important thing, you can say a limitation of the plain sailing is that this particular form of sailing, though it is very simple and easy using plain trigonometry, It can be used for distances which are less than 600 miles. Sumit beta, can you mute your mic? Thank you. Now, why is that so? The reason for this is that you see we have used plane trigonometry for calculating our courses and distances. When we are actually moving on the surface of Earth, we are not moving on a plane surface.
Sir, not able to see the presentation.
Beta, what about other candidates? Can you see the presentation?
Yes, sir.
Yes, sir.
Right.
Still on
Can see.
Yeah, you will need to log out and log in again, beta.
It is still on plain sailing or it is changed?
We are on plane sailing, showing 4 triangles for 4 quadrants.
Yeah, then it's fine.
Okay. Oh, the Earth is a sphere. So the surface of Earth is not a plane 2-dimensional surface. The surface is a curved surface. A 3-dimensional curved surface of the sphere. So when you use plane trigonometry on the curved surface, errors are bound to occur. So in these calculations, errors are bound to occur. However, till the time the distances are small, to be precise, when the distances are less than 600 miles, the errors which are introduced are so small that they can be easily neglected. The resolution, the error is not so great that it is going to affect our sailing, so it can be easily neglected. However, when the distance exceeds 600 miles, the errors become appreciable and we need to consider them. So this sailing is used only for distances less than 600 miles. So for our normal passage planning, when the distances involved are much lesser than 600 miles, we can easily use this plane sailing to calculate the courses and distances. However, when you are going on transocean passages and the distances exceed this amount, then in that case the plane sailing should not be used. Either we should use the great circle sailing, or if you want to still do rhumb-line sailing with distances greater than 600 miles, we should be using what we call as Mercator sailing. So that is the next form of sailing which we are going to see. So now we come to the third rhumb-line sailing, that is the Mercator sailing. Why do we have another form of rhumb-line sailing? We have already done that using the plane sailing. I already answered that question. That is because the plane sailing has a limitation. It has a restriction that it can be used only for 600 miles. More than 600 miles, using plane trigonometry on a curved surface, a 3-dimensional curved surface of the Earth, introduces appreciable errors which are significant and cannot be neglected anymore. So we use Mercator sailing. Mercator sailing gives us accurate result irrespective of whether the distance is less than 600 miles or greater than 600 miles. Now the second question is, how do we do or solve the question using Mercator sailing? Now to understand it very simply, whenever we use trigonometry, solving a right angle triangle, we have to have the 3 sides of the triangle measured in the same units. If you are measuring hypotenuse in centimeters, the base and perpendicular should also be measured in centimeters. So that is the basic principle of trigonometry. We cannot change the units. We cannot measure one side in centimeters and another in inches. the ratios will not work. Sin theta, cos theta, tan theta are not going to work that way. So if you remember in the plane sailing triangle, the units which we used were the latitude scale units. We used the latitude scale units. Let me show you here. Let's consider this is our initial position A. Let's consider this is our final position B. Let's make the plane sailing triangle. This is the plane sailing triangle which we used. The third vertex was named C. This particular angle was the course. This side, the hypotenuse, is the distance side. The vertical side, AC, is the D lat. And the horizontal side on top, that is B to C, was the departure. Now, if you look carefully, distance is measured as minutes of latitude. 1 minute of latitude is equal to 1 nautical mile. So we measure this side in units of latitude. Coming on to the vertical side, AC, we measure it as D lat. Now D lat, or difference of latitude, is also measured in terms of latitude units. The D lat between two places is the number of times 1 minute of latitude can be placed. The minutes of latitude between the two places, again measured on the latitude scale. The third side which we have was the departure. And you see, again, I told you departure is the actual east-west distance between any two positions. So all distances are measured on the latitude scale. So you see, we measured all the three sides of this triangle in latitude units. Now in Mercator sailing, a simple way to understand it is that we convert from latitude scale to longitude scale. We will measure the sides in the longitude scale. How do we do that? Let me show you the Mercator triangle now. The blue color triangle which you see, bigger than the red one, is the Mercator triangle. And in this triangle, let's name the vertices as D and E. Now the side DE which we have is the D long between our initial and final positions. So you see the D long is measured using the longitude scale or minutes of longitude. So we have not measured it as departure, we have measured the east-west stretch between our initial and final position in the longitude units as D long. Now coming on to the vertical side, the vertical side now becomes AE, alpha echo. Now this vertical side, how to measure this side in longitude units? It is measured as what we call DMP, difference of meridional parts. What is this DMP? As is clear from the name, it is the difference of meridional parts between A and B. Meridional part is nothing but 1 minute of longitude. 1 minute of longitude is also known as a meridional part. So measuring this side in DMP basically tells us how many minutes of longitude can be placed between A and B's latitudes. How many minutes of longitude can be placed between A and B? So this is the meaning of DMP, difference of meridional parts. How many minutes of longitude can be placed between the parallel of our initial position A and the parallel of our final position B. So you see we have measured the side AE, the vertical side, in longitude units. Now coming to the third side of the triangle. Now the third side was distance. Now there is no way that we can measure the distance in longitude scale because the units of distance are fixed. The distance is measured in nautical mile, and 1 nautical mile is fixed as 1 minute of latitude, 1852.3 meters. So there is no way we can measure the distance in longitude scale. So in Mercator sailing, the third side is left unnamed. We neither use this for any calculations, nor it is found out using the Mercator sailing formula. So the third side of the triangle, that is AD alpha delta, which is the hypotenuse side, is not defined or not mentioned or not used, not calculated in the Mercator sailing triangle. Now, how do we use these two sides to get the accurate course and distance?
Sir, for
Now,
Mercator
for this, again, we use the trigonometric ratio. The ratio is tangent course. Now, in this case, the tangent course will be perpendicular, which is the d long, divided by the base, which is the dmp. So you see the formula here, tangent course equal to d long upon dmp. Go ahead, beta.
Sir, what is the final, initial and final position we are taking in this triangle?
Beta, the initial and final position remains A and B only. The blue triangle has been made bigger just to signify that it's a different kind of triangle. It's a separate triangle. The final positions remain the same on the chart. Alpha to Bravo, they remain same. Only thing we are changing are the units.
Okay, sir.
Okay, that's why when you measure the DMP will be greater than the minutes in DLAT. So that's why this side has been shown bigger. Numerical value will be bigger, but the positions are exactly same where they were. Right, beta?
Okay, sir, got it.
Okay, let's move ahead then. This is the only formula which we use in Mercator sailing, the only formula. Now, one question may arise in your mind that we have calculated the course. If we know the initial position, we know the final position, we can find out the d long between them. We can also find out the dmp between them. Now, at this moment, a doubt may be arising how to find the DMP. I will tell you a little later. So we can find the D long and DMP and the course can be obtained. What about the distance? As I said earlier, we have not defined the distance in this triangle, the bigger blue color triangle. So how do we calculate the distance? For calculating the distance, we go back to the plain sailing formula. That is dlat equal to distance cos course. So once the course is calculated using the Mercator formula, the course is input in the plain sailing formula. Here we know that dlat between the two positions, initial and final latitude, is known, and putting these two values, the distance can be calculated. So the plain sailing formula for dlat is used to calculate the distance. Now, one important thing here, as far as trigonometry is concerned, mathematical calculation is concerned, you could have used the departure formula also. Departure is equal to distance sine course. So you can put the value of departure, you can put the value of course, and the distance would be known. But we do not use that as far as navigation is concerned. Why don't we use that? Because departure as a quantity is not actually present on our chart. What is present on our chart is either the dlat or the d long. So principally we do not use the departure formula for calculating the distance. So mathematically that's correct, it will give you correct answers, but fundamentally always use the the dlat formula for calculating the distance using Mercator sailing. Another doubt which could arise in your mind is that since we have used the plain sailing formula for calculating the distance, how do we attain the accuracy, the required accuracy in this case? Now the accuracy is obtained, you see, the course which has been used here has been calculated using the Mercator formula, not the plain sailing formula. So this course which we have calculated is a more accurate course. Once this is used in this formula, it gives you a more accurate distance. So the error in the course and distance is eliminated, which came because of using plane trigonometry. Another doubt which could arise in your mind is that in this form of sailing also we have used a right angle triangle only, and we have used plane trigonometry here also. So how do we attain the accuracy? The accuracy is basically attained using these DMPs, difference of meridional part. The DMPs account for the curvature of the earth. So when you get the DMP, difference of meridional part, it accounts for the curvature of the earth and brings in the required accuracy. The second way you could understand it from the chart point of view is, you see on a Mercator chart, 1 minute of longitude is a fixed quantity. You go anywhere on the Mercator chart and you measure 1 minute of longitude, it is a fixed dimension, fixed length. The latitude is not so. Depending upon where you are, at the bottom of the chart or at the top of the chart, 1 minute of latitude or 1 degree of latitude will vary in distance. 1 minute of latitude keeps on becoming bigger and bigger as you go away from the equator toward the poles. So 1 minute of latitude is a variable unit on the Mercator chart, whereas 1 minute of longitude is a fixed unit on the Mercator chart. So when you convert to longitude units in Mercator sailing, that gives you the required accuracy. Now to find out how do we obtain the DMP. Before I go to the meridional parts table, anything you want to ask up to here, beta?
Sir, just one small request. You had said something in the last, it was coming blur in my laptop. I think there was some communication, some problem with this thing. आपने यूं कहा था कि यही दोनों फॉर्मूले यूज करने DLong के. Last you said something about that 1 minute of DLong equals to something. I was not able to catch that. Can you please repeat?
Beta, I said that 1 minute of longitude remains constant all over the Mercator chart. Anywhere you go, 1 minute of longitude dimension remains constant, remains fixed, whereas 1 minute of latitude keeps on changing.
Understood, sir.
Okay. So when you obviously
these
use
are the
the
charts which we are using.
Yeah, when you use the longitude scale, since the unit is a fixed unit, that gives you the required accuracy.
Understood, sir.
Right, beta?
Yes, sir. Thank you.
Okay. Let's move ahead. To obtain the DMP, difference of meridional parts, we refer to the Norris nautical tables. In the Norris nautical tables, we will find meridional paths table. This meridional paths table gives us the meridional parts for any latitude. You can see this meridional paths table on the screen. This table is entered with the latitude. You can see the degrees mentioned on top of the table. The minutes are mentioned on the sides, on the vertical axis. The minutes are mentioned. So for any particular degree and any particular minute of latitude, its meridional parts can be found out. Now, once you have the meridional parts for your initial latitude, starting latitude, and the meridional parts for your final latitude, the destination latitude, they are combined together to get the DMP. Now, what do I mean by combined together? By combining, I mean they can either be added or subtracted. How do we decide whether the meridional parts are to be added or subtracted? If the latitudes are of the same name, both the positions are in the northern hemisphere or in the southern hemisphere, the smaller one is subtracted from the bigger one.
and we get the DMP. And when both the positions are in different latitudes, one position is in north hemisphere, the other one is in southern hemisphere, in that case the meridional parts are added up to get the DMP. If you see, it is exactly like how do we obtain the difference of latitude between two positions. If both the positions are in the same hemisphere, the smaller latitude is subtracted from the bigger one. If both positions are in the opposite hemispheres, we add up both the latitudes to get the DLAT. Exactly in the same way, we get the DMP, difference of meridional parts.
Now, beta, this meridional parts table is available in the Norris tables. And if you don't have Norris table, then I have shared a couple of tables, some of the tables, selected pages from the Norris tables on the WhatsApp group. So you can take a printout of those pages. It's about 20-25 pages or so. So if Norris table is not there, just take a printout of those pages and keep with you all the required information which we need is there in those 25 pages. So I hope up to here is clear.
Sir,
Go ahead.
For the exam point of view, these pages which you have shared are sufficient, or are we supposed to carry the entire table along with us when we are going for the paper?
No, beta, you are not required to carry it. MMD will provide you with the Norris table.
They will give this table.
Okay.
They will provide you with the table. They have their own tables, beta. Even if you carry your own table, they may not allow you to use them.
सर वो फुल टेबल नहीं देंगे, इसके जो मिडिल पार्ट्स के पेज हैं 15-16 वही देंगे बस सर.
Okay, all right. So I'm not sure beta whether they are giving selected.
सर बहुत सारे फॉर्मूलेज होते हैं ना, फुल टेबल नहीं देते सर नोटिस टेबल.
That's foolish beta. You are supposed to. Yeah, okay, all right, no issues.
So can you please tell one time more how to see the meridional parts in this table, sir, one time?
Any unit for this DMP?
No units beta. These are difference of meridional parts. These are basically minutes of longitude. We don't put any units against them. So to enter into this table beta, if you see the top part of the table, you see the latitude in degrees, and on the vertical axis you have the minutes. So for any degree and any minute, you go to that particular value and pick up the number.
Okay, sir. Thank you.
Right.
So basically, we get one value from one latitude of this DMP. We get another value from other latitude, and we add or subtract it as per the convention, right?
That's right, beta, to get the DMP.
Okay, sir, got it.
Okay, beta, great. So shall we move ahead?
One slide back.
Bolo beta.
Sir, one slide back करोगे बस उसका screenshot लेना sir.
Okay, all right, I'll do that. Now one thing beta, whenever you are doing a GC or composite question and they tell you to calculate the rumb line distance, so in that case a doubt may arise in your mind, shall I use the plain sailing or shall I use the Mercator sailing? So in that case always use Mercator sailing. A reason for that is usually great circle and composite is done for long distances which runs into thousands of miles. So if you use plain sailing, it may give you a substantial error. So always use Mercator sailing to calculate rumb line distance if required for comparison with GC or composite, right?
Sir, today there was one question in the questionnaire which you sent. There was one question. They were just solved using DMP.
That's right. There is a question which will tell you to calculate rumb line distance. So use this Mercator sailing for that.
Okay. So okay.
Okay, beta.
Yes,
so this was the slide which you were looking for?
Yes, sir. Yes, sir.
Right, beta.
So the last thing which you have told us in the case of in-case exam, when we had a confusion where we have to use plain sailing or Mercator, we have to use Mercator, right?
That's right, beta. Mercator. Whenever you have confusion, use Mercator.
Okay, thank you, sir.
सर इसमें हमने 10 cos to d long upon dmp किया सर.
That's right.
सर उसमें पहले वाले में था d long upon departure upon delet था सर. पहले departure upon delet
That's
था.
right, beta. Red triangle was the plane triangle, departure upon delet.
यस सर. तो सर ईस्ट वेस्ट जो भी सर डिस्टेंस होती है सर वो डिपार्चर होती है ना सर, उसको डी लॉन्ग कैसे ले लेंगे सर हम?
मैं समझा नहीं बेटा तुम्हारा क्वेश्चन, फिर से पूछो.
सर इसमें मार्केटर में E to D we took D long sir.
That's right.
And C to B is departure sir.
Right.
तो सर ईस्ट वेस्ट जो भी डिस्टेंस होती है सर उसको हम डिपार्चर मानते हैं ना सर नेविगेशन में?
ओके, दैट इज राइट बेटा. अगर आप डिस्टेंस मेजर करोगे ना तो डिपार्चर ही आएगा, लेकिन अगर आप इसे लॉन्जिट्यूड स्केल में मेजर करोगे तो डी लॉन्ग आएगा बेटा.
ओके, सो वी आर मेजरिंग लॉन्गिट्यूड स्केल सर.
दैट इज राइट. जो हमने ब्लू ट्रायंगल बनाई है मार्केटर के लिए, इसके सारे पार्ट्स को हम लॉन्जिट्यूड स्केल पे ही मेजर कर रहे हैं, हम लैट स्केल यूज नहीं कर रहे हैं मार्केटर में.
ओके सर, परफेक्ट सर.
ओके, ग्रेट. सो शैल वी मूव अहेड नाउ बेटा? So I'm removing this slide now. We are moving ahead. Okay. Now, beta, after this, the next topic which we have is basically we are jumping into celestial navigation now. So let me open up the slide. Okay, so beta, now we are moving into celestial navigation. We have done the sailings. In fact, we have done all 5 sailings: great circle, composite, parallel, plane, and Mercator. And now I am going to familiarize you with some basic stuff in celestial navigation. This also you have done in pre-C, again you have done in second mates, but I'm revising it once again so that any doubts are there, they will be clarified. इनमें जो basic चीजें आएंगी, they will be number 1, altitude correction. What are the corrections which we apply? And after that we will go into the almanac. We will see all the information which is there in the almanac. We will also see a little bit about chronometer ambiguity. What is this 12-hour chronometer ambiguity? And then I will familiarize you with the amplitude and azimuth formula. So all these calculations are used in our question number 5 and question number 6. One of these questions will involve these calculations. So it is important that we do not have any doubts related to them. So I'm going to go into the presentation now. You can have almanacs with you now, beta. You can keep almanacs with you wherever required. The almanac can be referred, right?
Yes, sir.
Right, beta. So I'm setting up the presentation now.
कैरेट शिप की अल्पनाक सर काफी फट गई.
Good, beta. That shows the effort which you have put in. So, okay, so we are going into the first altitude correction basics. So let us revise the altitude correction. Now the first basic concept which we are going to see is the altitude correction. So as I told you before, the altitude what we obtain from the sextant is the sextant altitude, and the altitude what we require for our side solving purpose is the true altitude. So altitude correction is the process of correcting the sextant altitude to obtain the true altitude of a celestial body. So let us see now what all corrections are applied to the sextant altitude to obtain the true altitude. So we obtain the sextant altitude of the body using the sextant,
The first correction which we need to apply to this sextant altitude is the index error. Now, what is this index error? This index error is basically the error of the instrument. Now, the sextant is a very complex equipment, having very sensitive equipment and very precise equipment. There are a lot of moving parts in the sextant, and because of those moving parts, there is a scope and there is a chance that those moving parts may be disturbed from their original locations, giving rise to some errors. These errors are basically the errors of the instrument. So this instrument error of the sextant is known as the index error. Now, as far as our MMD questions are concerned, this index error is provided to us in the question itself, and we need to apply it to the sextant altitude. Now, how is the index error applied? The index error is defined as either on the arc or off the arc. Now, if it is mentioned to be on the arc, the index error should be negative. So you can see here in the explanation, if the index error is on, that means the correction is negative. And if the index error is off the arc, that means the correction is positive. Now you can easily memorize it and remember it in terms of a light switch. Consider the index error as a light switch. If the switch is on, you put it off. If the switch is on, you put it off. Putting it off means negative or subtracted. And if the switch is off, you put it on. Putting it on means it is to be added or the correction is positive. So index error, the error of the instrument, it is negative if it is on the arc, and it is positive if it is off the arc. Now, once you apply the index error, the altitude what you obtain is the observed altitude of the celestial body. The next correction which we apply to the observed altitude is the dip correction. Now this dip correction is based on the height of eye of the observer. This is based on height of eye, and this dip correction is always negative. The dip correction is always negative, and it is based on the height of eye of the observer. Now, where do we obtain this dip correction? I will show you the dip correction in the later slides. In the coming slides, I'll show you the dip correction is obtained from the dip correction table given in the Nautical Almanac. So this is the second correction which we have applied. Once we apply the dip correction, we obtain the apparent altitude of the celestial body. Now to the apparent altitude, we have to apply 3 more corrections. The first one among them is the refraction correction. The refraction correction is basically due to the refraction of the light through the atmosphere. Whenever we see a celestial body, we are able to see it because some light from that celestial body is able to reach to our eyes. So that light obviously has to pass through the atmosphere. All the celestial bodies are in space. So any light coming from a celestial body to our eye has to pass through the atmosphere. Now when it passes through the atmosphere, it undergoes what we call as refraction. The ray of light coming from the celestial body suffers refraction or undergoes refraction. Refraction is a physics principle which says that whenever the light passes through 2 different mediums having different densities, it will either bend towards the normal or away from the normal depending upon the densities. So when the light is traveling in space, that is one medium, the density is 0. And from space, it enters into the atmosphere. Now atmosphere has some positive density, so the light bends towards the normal. Now this refraction correction is always negative. Because of refraction, the celestial bodies appear slightly higher than where they actually are. So this correction is always negative. The second correction applied to the apparent altitude is known as the semi-diameter correction. Now what is this semi-diameter? The true altitude of a body is measured with reference to the center of the celestial body. Now stars as well as planets, they appear to our eye as point objects. So when you take their altitude, you are automatically taking the altitude of the center of the celestial body. But that is not the case with the sun and the moon. Sun and moon do not appear as point objects. In fact, they appear as disks. So now the center of the disk is not visible to us. It would be very good if there is a dot in the center of sun and moon and we can directly measure the altitude up to that center, but that's not the case. So we are not able to identify the center of the sun and moon using our eye. So what we do in the case of sun and moon is we either take the altitude of the lower part of the disk of the sun or the moon, or we take the altitude of the upper edge of the disk. Now this is also known as lower limb or upper limb. Now when you take the altitude of the lower limb, obviously to reach up to the center of the body, you will have to add the radius of the body as visible to you. Now this radius in terms of altitude correction is known as semi-diameter. We know diameter upon 2 is what the radius is. So in navigation terms, it's not called as the radius, it is called as the semi-diameter. So the semi-diameter correction for lower limb will obviously be positive because from the lower limb, you have to reach up to the center of the body, so you have to add the semi-diameter. And if you take the observation of the upper limb, then the semi-diameter correction will be negative because from the upper limb you need to come down to the center of the body by an amount equal to the radius or the semi-diameter of the disk of the moon or the sun. So this semi-diameter correction is applicable only in the case of sun and the moon. There is no semi-diameter correction in case of stars and planets. Now the third correction which we apply to the apparent altitude is the parallax correction. Now parallax is the angle at the center of the celestial body subtended by the radius of the earth. That is what we call as parallax. And this parallax correction is always positive. So you can remember P with parallax, P with positive. So parallax correction is always positive. Parallax is the angle at the center of the celestial body subtended by the radius of the earth. So these are the three corrections which are applied to the apparent altitude. Refraction, always negative. Semi-diameter, positive in case of lower limb, negative in case of upper limb. And the parallax correction, which is always positive. Once you apply these three corrections to the apparent altitude of the body, what you obtain is the true altitude of the body. Now, the three corrections which we saw to be applied to the apparent altitude, refraction, semi-diameter, and parallax, these ones, they can be easily applied as a single correction. We do not need to apply them separately, one by one. That would be unnecessarily lengthy, cumbersome, and more time taking. We can apply all these three corrections in a single correction, and they are available to us in the Nautical Almanac. So when you apply all these three corrections using a single correction, it is known as total correction. Now, total correction can be easily obtained from the almanac, and it consists of all these three corrections in it. That is refraction, semi-diameter, as well as parallax. So the total correction gives us a very quick and easy method to correct the altitude of a celestial body. The individual correction methods are usually referred to or used during your pre-C training, because that's when you need to be clear about the concepts. But once you come to second mates or phase 1 level, the individual correction method is not usually recommended. The questions can be easily solved using the total correction obtained from the Nautical Almanac. So this is the complete altitude correction process. We start with the sextant altitude. First correction is the index error. It is negative if it is on the arc, and it is positive if it is off the arc. The second correction is the after applying the index error, we obtain the observed altitude of the body. The second correction which is applied is dip correction based on height of eye and is always negative. Then we obtain the apparent altitude. The three corrections applied to apparent altitude are refraction, which is always negative, semi-diameter, which is positive for the lower limb, negative for the upper limb, applicable only in the case of sun and the moon, and the parallax, which is always positive. All these three can be combined together in one single correction, that is the total correction. Once applied, let's go. Let us now see one by one how do we obtain these corrections. The first one which we applied was the index error, which I told you that the index error is given to us in the question itself. The value is picked up from there and applied. The second correction which is applied is the dip correction. The dip correction is obtained from the Nautical Almanac. If you open your Nautical Almanac, the first page of the Nautical Almanac looks like this. You have the first page of the Nautical Almanac, and on this page, the table which you see on the right hand side, the one which is highlighted now, this is the dip correction table. So you can see in this table, the height of eye is given in meters as well as feet, though feet is very rarely used nowadays. So the height of I is given in meters as well as feet, and against the height of I, you can see the value of the dip correction. So the dip corrections are tabulated here. There is a minus sign in front of all these corrections, reminding you that the dip correction is always negative. So you see a range of the height of I. Let us say you see a range from 6.6 to 6.9 meters, and within this range the value of dip correction to be applied is minus 4.6 minutes. Now in case you have the height of I falling at a critical entry means an entry which exactly matches with the table entry, let us say 6.9. So in this case there could be a doubt whether we should pick up minus 4.6 or minus 4.7. So out of these two, any value can be picked up. The difference will be only 0.1 minutes, which is a acceptable difference. But as per the convention, we pick up the upper value, the value which is upper in the table. So for 6.9, you can pick up minus 4.6 minutes. So this is the dip correction table. Moving ahead now, beta.
So on right side, na, it is given like 20 meter, 22 meter, and 24 meter.
That's right.
That table we have no. So in that table we have to interpolate, correct?
That's right, beta. If the height of I is more than 20, you see the format is slightly different. So there a range is not given, but the height of I is given after a certain interval. So if you fall in that range more than 20, you will need to interpolate. Okay, beta, got it?
सर सबसे टॉप पे वो 1 मीटर 1.5 वो भी इंटरपोलेट करना है क्या?
That is right, beta. Up to 3 meters interpolation is there. Then you see 2.4 meters to 21.4 meters. You have the big table. Then 20 meters onward again interpolation is there. Okay, so moving ahead now.
Sir, if it is more than 48, say 55 meters, then what is the difference we have to take for extrapolating?
No, you don't. You will not get a value more than 48 meters, beta.
Okay, sir.
Right. Okay, let's go ahead. Now, after the dip correction, the next correction which we require is the total correction. So let us now see the total correction for all celestial bodies one by one. As I told you, we have 4 celestial objects, celestial bodies available to us. That is the sun, the stars, the planets, and the moon. So let's open up the first page of the almanac once again, the same page which we saw in the previous slide. Now you can see the total correction for the sun. Let's first find out it for sun. You can see the total correction for the sun given on the left hand side in the first table. So you see the table which is highlighted. It gives you the total correction for the sun. The table is entered with apparent altitude as well as the limb of the sun. So you enter with the apparent altitude. There are 2 corrections given against each apparent altitude, or for a range of apparent altitudes, 2 corrections are given. The first correction is for the lower limb of the sun, and you can see a positive sign in front of it. And the second column gives you the correction for the upper limb of the sun. You can see a negative sign for the upper limb total correction. Now, one more thing which you will observe here is that the total correction table of the sun is divided into two parts. The first part of the table gives you the for the period between October to March, and the second part of the table gives you the correction between April to September. So basis the date on which you have taken the site, you will be entering the appropriate part of the total correction table. Check the date for which the what is given in the question on which the site is taken, and basis that date you enter into the appropriate part. Enter with apparent altitude. Out of these two corrections, pick up the correction for the limb which is given in the question. Lower limb corrections are positive, upper limb corrections are negative. Now moving to the second celestial body, that is the stars, and the next one, that is the planets. Now for stars and planets, we have a single table. The second table which you see on the first page of the Almanac gives you the total correction for stars as well as planets. This table is also entered with apparent altitude. So you enter with the apparent altitude, and for a range of apparent altitude, the total correction value is given here. All the total correction values are negative. So the second table gives you the total correction for stars as well as planets. Now, when you are picking up the total correction for planets, you have to be careful about two planets, that is Venus and Mars. Now, whenever the altitude correction is being done for Venus and Mars, once you have referred to the total correction table, obtained the total correction against the apparent altitude, after that you have to apply an additional correction also. You see the additional correction value is mentioned here in the second part of the table. This additional correction also has to be applied to these two planets, that is Venus and Mars. Now, how is this correction applied? You can see for every planet, say for Venus, they will give you a range of dates. In the first part they have given January 1 to December 10. The apparent altitude between 0 to 60, the correction is plus 0.1 minutes. Then in the second part, they say December 11 to December 31. From 0 to 41 degree apparent altitude, the correction is plus 0.2. For 41 to 76 degree apparent altitude, the correction is plus 0.1 minutes. So the correction has to be picked up from the second part of the table, the additional correction, and the additional correction has to be applied in addition to the total correction obtained from the total correction table against the apparent altitude of the body. Now, important thing to understand here is this additional correction, as is clear from the name, is additional to the normal correction. The normal correction given on the left hand side part of the table against a range of apparent altitudes. The additional correction is over and above the normal correction. Please don't forget to apply the normal correction. It should not happen that you apply only the additional correction and you forget about the main correction. So it is applicable only in the case of Venus and Mars. Now a doubt may arise in your mind. What is this additional correction for? Now basically Venus and Mars are closer to us compared to Jupiter and Saturn, which are the other two planets used for celestial navigation. Being closer to us, they appear slightly bigger, and just like moon, it is possible that they may be showing phases. You may not be able to see the complete planet, but you may be able to see some part of the planet, just like you can see the phases of the moon. Sometime you see the full moon, sometime you see a gibbous moon, sometime a crescent moon. So that way there could be this phase effect with these two planets also. And other than the phase effect, these planets are very close to us. So they have a substantial parallax, which is a positive correction. The parallax of these planets could also be substantial. There is no parallax for Jupiter and Saturn. They are too far away from us. So the radius of the Earth does not subtend a suitable angle. But for Venus and Mars, there could be a little bit of parallax. So this additional correction takes care of both these small corrections, that is the phase correction and the parallax correction. These are not applicable to Jupiter and Saturn as they are far away, they do not show the phases, and they do not have any parallax. They are not applicable to the stars either, because stars have their own light, they emit their own light, so they don't show any phases. And secondly, stars are so far away that parallax for stars is nil. So this was the total correction for the sun, for the stars, and for the planets.
सर जो ये एडिशनल जो अपना करेक्शन है, इसके लिए जो अपरेंट ऑल्टीट्यूड देखेंगे वो आफ्टर डिप वाला ऑल्टीट्यूड देखेंगे, या डिप के बाद जो अपरेंट ऑल्टीट्यूड है उसके बाद जो लेफ्ट साइड में जो करेक्शन है वो ऐड करके फिर जो ऑल्टीट्यूड आएगा उसके रेफरेंस में देखेंगे ये वाला?
बेटा ये जो दोनों की दोनों करेक्शन है स्टार्स एंड प्लैनेट्स के लिए, दोनों की दोनों करेक्शन दे आर चेक्ड अगेंस्ट द अपरेंट ऑल्टीट्यूड.
Okay sir, means the altitude which we get after dip only.
That is right. You apply the index error, you apply the dip, you will get the apparent altitude. That is the altitude with which you enter into these tables.
सर आप बताए थे एग्जैक्टली 6.6 मीटर डिप रहेगा, तो कौन सा लेंगे सर, नीचे वाला या ऊपर वाला? -4.6 और -4.5 सर?
-4.5 बेटा, ऊपर वाला.
ऊपर वाला लेंगे सर, राइट?
That's right.
6.9 रहेगा तो -4.6.
That's right बेटा.
ओके सर.
सर ये
but won't make much of a difference. 0.1 का ही difference है.
That's right beta. Even if you take the lower one, it will still be considered accurate.
और सर ये इसमें अपरेंट एल्टीट्यूड के केस में भी आएगा, अगर मान लीजिए एग्जैक्टली 9 डिग्री 56 मिनट है या फिर 10 डिग्री 08 मिनट है तो -5.3 हम लोग ऊपर वाला लेंगे, ऐसा कुछ है क्या?
That's right beta. You take the upper value in apparent altitude also, in total correction also.
Okay.
So in the case of Venus, we have to put these two corrections, apparent altitude correction and plus this additional correction also, right?
That is right, beta. Two corrections in case of Venus and Mars.
Okay, sir. Thank you.
Okay, beta. Great. चले आगे, मून पे चले?
Yes, sir.
Very good.
चलो सर.
Mars पे जाने.
Let's now see the total correction for the moon. Now, moon is the celestial body which is nearest to us, the nearest celestial body. The more closer a celestial body to us, the more complicated its apparent motion becomes. So you will see that all the things associated with moon are slightly more detailed, slightly more complicated as compared to sun or the stars or the planets. The total correction for the moon is given on the last page of the almanac, and it extends to 2 pages. You can see the last page of the almanac now giving the altitude correction for the moon. Now this total correction table is divided into two parts. You see the upper part of the table, which gives you the main correction, and you see the lower part of the table, which gives you the HP correction. What is this HP? HP is the horizontal parallax. This is the parallax of the moon when the moon is on the horizon of the observer. So let us see both these tables one by one. Let's zoom into these tables, the upper one and the lower one, and see how these tables are referred to. Sumit beta, can you mute your mic? Okay, thank you. Now the values, the tables which I'm showing you, values may be slightly different from 1992 Almanac. I picked up a recent Almanac for this. So don't worry if the values are different slightly. You can see the upper part of the table now. Now this upper part of the table, which gives us the main correction, is entered from top using the apparent altitude. So apparent altitude has already been obtained by applying index error and dip correction. So you enter into the top part with the apparent altitude. You can see every column gives you a range of 5 degrees of apparent altitude. So from 0 to 4 degree 59 minutes, then 5 degrees to 9:59, then 10 to 14:59, 15 to 19:59, and so on. Depending upon what your apparent altitude is, you enter into one of these columns and you pick up the main correction from this part, upper part of the table. Let's say, for example, your apparent altitude was 3 degrees and 50 minutes. So you will be entering into the first column. You see 0 degrees, then 1 degree, 2 degree, 3 degrees. And then on the side, you can see the minutes, 0 minutes, 10, 20, 30, 40. So for 3 degree 50 minutes, the correction is here, which is 56.1 minutes. So this is how you obtain the main correction. There is a dip correction table given here alongside. But this dip correction table is a little shortened. So I would recommend you use the table given on the first page. It is not that this dip correction table is applicable for moon. Dip correction has got nothing to do with the celestial body. Dip correction depends only on the height of eye of the observer, and it is the same for all celestial bodies. So you can refer to the dip correction table given on the first page itself for the moon's dip also. Now let's see the bottom part of the table.
Sir, one doubt.
You can see the bottom part of the table. Go ahead, beta. Go ahead.
So this 56.1 is positive, right?
Both the corrections are positive, beta.
Okay.
Top and bottom, both corrections are positive. I'll explain to you. Here, the same column which you entered from top, you go down into the same column for picking up the HP correction in the bottom part. Now, when you enter into the bottom part, you will see two columns, two sub-columns in every one column of the upper table. One is represented by L and another is represented by U. It stands for the lower limb and the upper limb of the moon. So depending upon whether the altitude is of the lower limb or the altitude is of the upper limb, you will enter into one particular part. And when you come down, you will see on the sides, the HP values, horizontal parallax values of the moon are mentioned. So when you come to this part of the table, first you find out whether it is upper limb or lower limb. Let's assume in our particular case, it was a lower limb observation. So you enter into the L part of the column and then you look for the HP of the moon, which was there at the time of the sight. Now, how can we find out the HP of the moon? The HP or the horizontal parallax of the moon is given in the almanac for each and every hour of the year. So once I go to the daily page of the almanac, I will show you the HP value there. So this horizontal parallax is picked up from the daily pages, the date pages of the almanac for the date on which the sight was taken, for the hour for which the sight was taken. So the HP was 54.3 minutes. So you can see for the lower limb and for a HP of 54.3, the HP correction is 0.7 minutes. So you have obtained the upper correction, which was 56.1 minutes. You have obtained the HP correction, which was 0.7 minutes. Now both these corrections are positive. Both these corrections are positive. They have to be added up. Now once you add up, after that one more thing has to be seen. If it was a lower limb observation, the altitude was of the lower limb, you add these two corrections and you will obtain the true altitude of the moon, or you will obtain the total correction for the moon. But in case if this was the upper limb of the moon, then you have to subtract 30 minutes in the end. You can call it a upper limb correction, and 30 minutes have to be subtracted from the altitude of the upper limb to obtain the true altitude of the body. So to summarize, you get the main correction from the top part of the table. You get the HP correction from the bottom part of the table. Both these corrections are positive. If it is a lower limb observation, apply these two corrections and you will obtain the true altitude. If it is a upper limb observation, after applying these two corrections, you have to subtract 30 minutes, can be considered as a upper limb correction to obtain the true altitude of the body. Now all this which I have explained is mentioned in this part here. You see, 30 minutes is to be subtracted from the altitude of the upper limb. So it is mentioned in this part here. If you have any doubts, you can just read this explanation given here and it will clarify how the table is to be used. So any more doubts in the table, beta?
सर इसका रीजन क्या है सर 30 मिनट्स माइनस करने का सर?
Okay, I'll explain to you little later, beta. Polaris पे जाएंगे ना, फिर मैं आपको explain कर दूंगा इसका मतलब क्या है, why this 30 minutes is there.
Okay sir.
Okay, all right. So चलें बेटा, आगे चलें?
Yes sir.
Very good. Let's now move on to the next basic concept, which is the chronometer time ambiguity. Now let's first understand what is this chronometer time ambiguity. The chronometer is a highly accurate clock which is set to the GMT, and whenever you take a sight, you can obtain this GMT from the chronometer. Now the catch here, as you can see in the diagram, the chronometer has a 12-hour dial. The dial of the chronometer is only 12 hours, it's not 24 hours, so it gives you the time in 12-hour format. Now the clocks which we usually have in our homes also give us the 12-hour format time, but there is no ambiguity in those clocks because whatever time it shows, there are two possibilities. It could be AM or it could be PM. Let's say if the clock shows 1000 hours, it could be 10 AM or it could be 10 PM. Now at our home, we don't have any doubt because the position of the sun immediately tells us whether it is AM or PM. But the chronometer does not give you the time of the place where the ship is. The ship could be anywhere on Earth. It is giving you the time of the Greenwich meridian. So there is a possibility it could be 1000 hours or 10 o'clock in the AM, or it could be 2200 hours or 10 o'clock in the PM at Greenwich. So this is the 12-hour ambiguity which we have in the chronometer time. Now how is this ambiguity resolved? Now whenever the chronometer time is given to us in the question, with that a AM PM indication is always given. Whether it is AM on the ship or it is PM on the ship, that indication is always given to you. And it makes sense because whenever you take a site, you will be aware of whether it is AM on board or PM on board. So we use this information to resolve the 12-hour ambiguity. So what we do is we write down both the possibilities for the GMT. The two possibilities, GMT1 and GMT2, are written down. Now we apply the longitude in time to the GMT. Longitude in time. What is this longitude in time? The longitude can be converted into time by dividing it with a factor of 15. So whatever longitude you have, if you divide that longitude by 15, it will give you the longitude in time. Now from where do we obtain this factor of 15? We know there are total 360 degrees of longitude and the Earth completes one round in 24 hours. So 360 degrees, one round completed in 24 hours. If you divide 360 by 24, you get this factor of 15. So in 1 hour, the Earth rotates by 15 degrees. So this is the factor which we have. Divide the longitude by 15 and you get the LIT. What is the use of this LIT? LIT can be used to convert GMT to LMT or LMT to GMT. So what do we mean by apply? It can be either added or subtracted. Like in this case, we have the GMT. We can add or subtract the LIT to get the LMT. Now whether it should be added or it should be subtracted can be easily checked from the idiom. Longitude east, GMT least, longitude west, GMT best. So depending upon whether your longitude is east or west, you can find out whether the GMT will be least or GMT would be greater. And accordingly, you can use the plus and minus sign. Obviously, when the longitude is west, the GMT has to be best or greater. So you will obviously use a negative sign. And if the longitude is east, that means GMT has to be least. So it means you have to use a plus sign to obtain the LMT. Now once you apply the LIT, you will have two options of LMT, LMT1 and LMT2. Now these two options which you have obtained, check them with the AM PM indication given in the question. So whatever LMT is correct
as per the AM PM indication. One of these LMTs will be in the AMRs, the second one will be in the PMRs. So you find out which is the correct LMT by using the AM PM indication given in the question. Once the correct LMT is obtained, you can go back upwards and you can identify which was the correct GMT. That is the resolution of chronometer ambiguity. Nowadays, the practical use of chronometer has become redundant, and the change is evident in the questions which come in our papers also. Most of the questions, I would say 90% plus questions, are now based on GMT only, and you can straight away pick up the time without bothering about any ambiguity, 12-hour ambiguity in the time. But it may find way in some of the questions somewhere, and if it comes using this method, you will be able to quickly and easily resolve the chronometer ambiguity and find out the correct GMT time. So hope that is clear, beta. Chale aage?
Yes, sir.
Very good, beta. Great. Now there could be a date ambiguity in some of the celestial navigation questions. What do I mean by date ambiguity? They may give you a particular date in the question, and they may not specify to you whether this date is the or the GMT date. There could be two possibilities. It could be the date or it could be the GMT date. If it is specified in the question, then there is no doubt. Whatever they have specified, if they have specified it is the GMT date, you use it as per GMT. If they specify it as the LMT date, you use it as LMT. There is no doubt at all. However, in some of the questions, if it is not specified or not mentioned whether the date given is the local date or the GMT date, what is to be done? So for all these cases, always remember the date given in the question is always the LMT date unless specified otherwise in the question. So whatever date is given to you, you will always consider it as your local date or LMT date unless they have specified exactly that this is GMT. Only in that case it is to be used as GMT. In all other cases, when it is not specified, it is to be used as a LMT date. Now this is a very important statement and it will help you to resolve any doubt or any ambiguity which you may have in your mind related to the date of the question.
Rajkumar.
Okay, beta, let's go into the daily page now. Now let's move to the Almanac daily page and familiarize ourselves with the data given on the daily page of the Almanac. So on every daily page or every day page, there are two pages in the Almanac, the left hand side page and the right hand side page. Right now I have opened the top of the left hand side page. Now this one page serves
3 different days. As you can see here, this particular day refers to March 7th, 8th and 9th, Monday, Tuesday and Wednesday. So the data for these 3 dates is given on a single page. Now the first column which you see here gives you the GMT. This is the date, and then you have the hours from 00, 1, 2, 3, 4, 5, 6 up to 24. Then the first column which you have after the date and hour is the Aries column, and you have the GHA of the Aries given to you for every GMT hour. The GHA is given in degrees and minutes. So for any day of the year, for any hour of that day, you can obtain what was the GHA Aries or what will be the GHA Aries at that particular day and hour. Now, if you want to get the GHA for a particular minute also, for a day, hour and minutes, then to this hourly figure, you will have to apply the increment for those many minutes and second. So let us say you want to find out the GHA of Aries for 7th March, 06 hours, 30 minutes and 30 seconds. So up to 06 hours, the value is available here, 255 degrees, 23.4 minutes. For 30 minutes and 30 seconds, you have to go to the increment table. You have to get the increment from there and add that increment to this value. You will get the GHA Aries for any particular day, hour, minute and second in the entire year. The declination of Aries is not given because first point of Aries always remains on the equinoctial. Its declination is always 0. There is no change in its declination. After Aries, you have the 4 planets given to you: Venus, Mars, Jupiter and Saturn. The first figure which is given along with the planet name is its magnitude, the stellar magnitude, which gives us an idea about the brightness of these planets on that particular day. The brightness of the planets can change on a daily basis depending upon what is their location or position in the orbit around the Earth, around the Sun. The Earth and the planet both are revolving around the Sun, and depending upon the positions in their orbits, the brightness or magnitude of planets may vary. Now, under every planet column, you have the GHA and declination given to you for every GMTR. And as mentioned, in case of Aries, if you want it for a particular minute and second, you will have to add the increment. I'll show you the increment table in the coming slides. So you have the GHA and declination mentioned for all the planets. Then you come to the column on the right hand side. This is the column for stars. So you see a list of all the stars mentioned here. This list is given in alphabetical order, and this list gives you 57 selected stars. These are the 57 stars which are most often used for site taking, and they are given here for quick accessibility. Whatever date page you open, you will be able to get the star data from here. What is the data given along with the stars? They have given you the SHA, sidereal R angle, and the declination of each and every star on this page. The names are given in alphabetical order. You can see starting from A and going to B, C, D, and so on.
Sir, one doubt. In
Let's
the
now
previous
go.
page, the
Okay, beta, I'll go back. Go ahead, beta. What's the doubt?
yes, sir. So the sign convention used against the planets is the magnitude, like minus is
That's
minus
right, beta.
3.8.
magnitude number of the planet, Venus minus 3.8.
So that will be the more brighter than the Jupiter, right?
Yes, it is stellar magnitude beta. The stellar magnitude decreases as the brightness increases. So on this particular day, the brightest planet was Venus, followed by Jupiter, followed by Mars, and the least one, Saturn.
Okay, sir. Thank you.
Okay, we will do stellar magnitude in detail also later on. We will do that.
GHA Aries which is given, we will be using which GHA Aries, sir? The Venus example, they are asking for planet. So we will be using this GHA Aries, no? Like for 7 hour 00 minute, we will use 199 degree 13.8.
Beta, for
Not
planets,
the 165 one.
for planets, you do not need Aries GHA. Aries GHA is only required for stars.
Stars only.
Okay, so that GHA Aries is for a star. Okay, sir.
That is right. For planet, the GHA is directly given, beta. Okay, great. Shall we move ahead, beta? Bottom part पे चले?
Yes, sir.
Okay, let's go. Let's now go to the bottom part of the left-hand side daily page. This is the bottom part. The first column is the Aries column. And at the bottom of this column, you see they have given you the meridian passage of Aries. It's given as 12 hours, 53.4 minutes. This meridian passage is given in LMT. This is not GMT. The times given here with the date were the GMT times, but the time given at bottom, the meridian passage time, is in LMT. This is the LMT meridian passage of Aries. Now under the planet columns, you see 4 columns. These were for 4 planets: Venus, Mars, Jupiter, and Saturn. Under the planet column, you will see the value of V correction and D correction. Victor correction, V correction, and delta correction, D correction. What is this V and D correction for? V correction is used to obtain the GHA of a planet. The hourly GHA is picked up from the daily page. The increment for minute and second is picked up from the increment table. And after applying the hourly figure and the increment, you have to apply the V correction also. The V correction which is given here is for 1 hour, and for whatever minutes you are applying it, you will get the value for this particular V correction in the increment table. I'll show you the increment table after in the next coming slides. So this V correction is for 1 hour. The V correction which is to be used for that particular minute is given in the increment table. Same way, the D correction is applied to the declination. The hourly figure of declination is obtained from the daily page, the date page, and the D correction is applied for any minute and seconds. So this value of D given here is for 1 hour. The value which you require for any particular minute and second will be given in the increment table. So we have the V and D correction given for all the 4 planets. One important thing, if you have observed here, the V correction for Venus, this is the first planet, the first column is for Venus, it could be in the negative range. You see it is minus 0.6. Whereas the V correction for all the other planets is always positive. Then on the right hand side, you see bottom part, right hand side, you have the SHA of all the 4 planets. Venus, Mars, Jupiter, and Saturn, their SHA is mentioned here. And along with the SHA, the meridian passage time of the planets is also mentioned. This is the LMT meridian passage of the planets, LMT meridian passage of all the 4 planets.
सर जो V नेगेटिव है उसका मतलब जो
टाइम फॉर
वो माइनस होगा।
ग्रीनविच लेना सर।
ओके बेटा, जो V नेगेटिव है इसका मतलब है कि V करेक्शन माइनस होगा। You will have the hourly value, you will have the minute increment, they will both be positive, and this V correction increment will be negative for Venus.
ओके सर।
ओके, और बताओ बेटा, और क्या डाउट है?
सर ये हमारे पास टाइम जो LMT है, दिस इज LMT एट ग्रीनविच मेरिडियन, राइट सर?
That is right beta. If you go a little deeper into it, it is LMT at Greenwich Meridian, which is also a GMT time, but it is basically
at Greenwich
the
Meridian.
time of occurrence at the Greenwich Meridian.
Okay sir.
Okay, great. Beta right side page भी देख लें, maybe another 5-10 minutes.
Yes sir.
Yes, sir.
Okay, okay beta, all right. Let's now go to the right hand side page of the almanac. The right hand side page gives you the data about the sun. The first column is for the sun. You can see the GHA and declination of the sun given for all hours every day. So you can get the hourly figure of GHA as well as declination from the daily page. Then next column you have the data given for moon, and for the moon you have the GHA and the declination given for every hour. Now the difference which you will see for moon is you can see the V correction and D correction given for the moon on an hourly basis. It was not so in the case of planets. For the planets, there was a single V correction and D correction for the entire 3 days. But for the moon, as I told you, moon being closest to us is the most complicated of all. So the V correction and D correction for the moon is given for every hour because the V correction and D correction changes on an hourly basis. You can see the V correction at 00 hours was 7.7 and at 01 hours it became 7.8. Same as with the D correction, 8.3 becomes 8.4, 8.5 and so on. So this is the reason why the V and D correction for moon is given for every hour. And as I told you when we were referring to the total correction table for moon, the HP, horizontal parallax of the moon, is given on the daily page for every hour. So you can see the HP of the moon given here for 00 hours, it is 59.5 minutes. This HP is used for getting the HP correction of the moon from the total correction table. Now we go to the right hand side. In the next column you see we are given twilight times.
Sir.
हाँ जी बेटा बोलो.
Sir, can you explain the HP, sir? I just missed it.
Okay.
HP.
No beta, I just said that HP of the moon is given in the almanac for a hourly basis. Every hour you see the value of HP is given. You pick up the value from here and then you can use it to get the HP correction from the moon's total correction table. Okay beta, got it? Hello, got it beta? Okay, I think he got it. So let's move ahead. The twilight times are given to us. We have the nautical twilight and the civil twilight time given here. The twilight times and all the further times. Next you have the sunrise time. Then you have the moonrise time for all the dates, 7th, 8th, 9th, and one next day is also included here. That is the 10th. It is repeated on the next page also. All these times, whether it is the nautical twilight, civil twilight, sunrise, or moonrise, are in LMTs, local mean times. This is not referred to GMT. These are all LMTs, and they are given against the latitude of the observer. You can see starting from 72 degrees north, for every different latitude, you see the time is different. Let's go to the bottom part of the right hand side page now. We come to the bottom part of the table. This is the first column here. The first column was for the sun. Now at the bottom of this column, you see you have the semi-diameter of the sun given. In this case, it is 16.1 minutes. Now this semi-diameter is applicable for all the 3 days. It remains same, does not change on a daily basis. So 16.1 is the semi-diameter of the moon. May be required if you are doing individual corrections to the altitude. Then you have the D correction to obtain the declination for any minute between the two hourly figures. The D correction is given here. The increment for D correction is obtained from the increment table and applied. Now under the moon's column, you see the semi-diameter of the moon given. 3 values are given. These are the 3 different values for the 3 days. The first one for the topmost day, second one for the middle day, and the last one for the bottom day given in the daily page. So this is because the semi-diameter of the moon keeps on changing on a daily basis. You come to the right hand side. Now right hand side you see the first box for the sun. For the sun they have given you 2 parameters here. One is the equation of time. The equation of time is something related to the true sun and the mean sun, which we will discuss separately. So it is given for 2 times in a day, 00 hours and 12 hours, 11 minutes and 1 seconds, 10 minutes and 54 seconds given for the 7th day. And with the equation of time, you have the meridian passage time. This is the LMT meridian passage of the sun. So in this case 12:11, next day 12:11, next day it is 12:10. Coming to the right, you have the box for the moon. You have the meridian passage time of the moon given, upper and lower Marpas. Now this upper and lower basically stands for upper meridian passage and lower meridian passage. What is this upper and lower meridian passage? Upper meridian passage is on the observer's meridian. Lower meridian passage is on the observer's inferior meridian. Why is the inferior meridian Marpas time given here? This may be required or used in case the moon becomes circumpolar. So this time is used in circumpolar questions when the moon becomes circumpolar, and we are able to observe it when it is crossing the meridian or the inferior meridian of the observer. Next you have the age of the moon and the phase, how much percentage is visible. So the moon is on 28th day, 29th day and 00 day, and you can see it is a new moon day. The 9th is a new moon day. The visibility was 4% on 7th, 1% on 8th, and nothing is visible on 9th. So this was the information provided to us in the almanac.
Sir, in equation of time also, this time is in LMT?
Beta, equation of time is basically a duration. It is a 11 minute and 01 second of duration. It is the difference between the two suns. It is not showing you any time. It is showing you the interval of time.
Okay, sir.
Okay. So it is neither LMT nor GMT. It is just a difference between the true sun and the mean sun. I will be doing it in detail later on. Go ahead, beta. Next doubt.
सनराइज और मूनराइज में रेक्टेंगल बॉक्स बने हैं, ब्लैक और एम्प्टी बॉक्स है.
वेरी गुड बेटा, अभी बता देते हैं. Now, when we refer to the twilight or sunrise, sunset or moonrise, moonset columns, we may come across some special symbols used in the almanac. As you can see on this particular page, this is June 14, 15 and 16th, 1992. You can see here in the that there are some white boxes under the sunset column and also under the twilight. There are some slanting lines present here in the twilight column, and there are some black boxes shown under the moonset column. So what is the meaning of these special symbols? White boxes, black boxes, and the strokes, that is the slanting lines. Now the white box indicates that the sun or moon remains continuously above the horizon, or you can say that the sun or moon is circumpolar for that particular observer. The black box indicates that the celestial body does not rise at all. So depending upon whether it is below the sun column or the moon column, it indicates that sun or the moon does not rise at all for that particular observer. Or you can say it that it remains below the observer's horizon for the full day, full 24 hours. The third symbol which is used are the slanting lines or the strokes. The strokes or slanting lines indicate that the twilight lasts all night for that particular observer. You will see the slanting lines only under the twilight column, and they tell us that the twilight stays for the complete night. That means when the sun sets, the twilight commences, and the twilight stays till the next sunrise. So this is the meaning of the special symbols used. Clear, beta? Symbols clear?
Yes, sir.
Yes, sir.
Very good, beta. Great. Now let me just show you the increment table and then we will finish off for today. Let's now go into the increment table. You can see the screenshot of increment table for 46 minutes and 47 minutes. Now you see in the increment table, the first column gives you the seconds. So for each minute and every second, you can get the increment of HA for all the celestial bodies. The next column after the time column is the sun and planets column. So you see the increment of the sun and planets given in this particular column. Let's say, for example, for 46 minutes and 10 seconds, the increment of the GHA of sun or planets is given as 11 degrees 32.5 minutes. Now, after sun and planets, you have the Aries column. The second data column is the Aries column, and you can see the increment of Aries here. Why two separate columns for sun and Aries? That is because the rate at which the sun and Aries change their GHA is different. So just for your information, the sun changes its GHA at a rate of 15 degrees per hour, and Aries changes its GHA at a rate of 15 degrees 2.5 minutes. That's why the different columns, and you should be careful when you are picking up the increment values from here. You should pick up the value of the increment from the appropriate table as per the celestial body which you are looking for. In case of stars, it will be picked up from the Aries column, and in case of sun and planets, it will be picked up from the sun and planets column. The difference is evident if you see for 46 minutes and 10 seconds, the value for sun was 1132.5, whereas for Aries is 1134.4 minutes. The next column is the increment column for the moon, and you can see the increment values. The rate of change of GHA for the moon is different. The rate of change of GHA for moon is basis 14 degree 19 minutes in this particular table. That is just for your information. So you can see for 46 minutes and 10 seconds, the increment for moon is 11 degrees 1.0 minutes. So these three columns giving you the increment for the GHA of sun, planets, Aries as well as moon. Now coming to the next part of the table, you can see the next part of the table provides you the increment for V corrections and D corrections. So the V correction and D correction which were given in the daily pages or the day pages of the Almanac were for 1 hour. Now for any particular minute and second, you can find out the increment of V and D correction from here. Let us say, for example, if the V or D correction was given as, let's say, 7.4 minutes. V or D correction value was 7.4 minutes for 1 hour. Then in case of 46 minutes, the increment for that value would be 5.7 minutes. So you can see it here. For a hourly value of V or D, you have the increment which is applicable to this specific minute. So for 46 minutes, the increment for 7.4 D or V value would be 5.7. So this is what is used. The V correction is used for calculating the exact GHA, and the D correction is used for calculating the exact declination at a particular hour, minute and second. So clear beta? Any doubts up to here?
E और D में seconds का कुछ लिया दिया नहीं, only minutes.
That's right beta, only minutes. Okay, all right. So if you are comfortable, then I can close out the slide.
Yes, sir.
Yes, sir.
Very good beta. Great.
Yes, sir. Thank you.
Okay, so good. We covered up the basics today. सब याद आ गया बेटा? Second maths.
Yes, sir.
याद भी आया और बहुत
कुछ क्वेश्चन वोश्चन करने पड़ेंगे सर, ऐसे थोड़ी याद होगा।
वो भी करेंगे बेटा, उसका भी टाइम आएगा।
फिर भी सर जो किया था वो तो याद आ ही गया ना, भी यहाँ से करेक्शन लगाते थे, यहाँ से वी आर पिकिंग अप द वैल्यूज, यू नो।
राइट, बिकॉज बिना इसके तो फिर सवाल करेंगे तो गलत हो गए। राइट, सो जितना वो भूला हुआ था वो सब वापस याद आ गया है. सो वी आर गेटिंग रेडी फॉर द एक्चुअल क्वेश्चंस नाउ. So tomorrow we will, next class whenever we have, only few basics are remaining. So we will cover up those basics also, amplitude and azimuth calculation, and then we will move into side solving. So
The
great,
Polaris is
beta.
also remaining, right? Polaris.
Yes.
The Polaris is also remaining, right?
That's right, beta. All methods are remaining. Marpas, long bicron, intercept, x meridian, Polaris, सब करेंगे.
ये वाला सबसे टफ टॉपिक है ना सर?
नहीं बेटा, अभी तक काम.
अभी तक तो ठीक है सर, बट सुना हूँ बहुत टफ है. 5 और 6 क्वेश्चन नंबर 5
आगे
और
भी
6.
ठीक चलेगा बेटा, चिंता ना करो, आगे भी ठीक चलेगा, बस चलते जाना मेरे साथ साथ, बिल्कुल ठीक चलेगा, डोंट वरी. ओके, ग्रेट. So I will not waste any more time, so let's break off today and I'll see you in the next class.
Okay sir, thank you.
Okay, Jai Hind sir.
Yes, sir. Jai Hind. Jai Hind beta. Thank you beta. Bye bye.